Hey there, geographers. I hope you're doing really well. So, in this module, we're going to focus on atmospheric circulation and weather systems. What that boils down to is if you hear the word circulation, it means how something moves throughout a body or some sort of system. So, if you'll take, for example, like our own human circulatory system, you will learn about how various fluids or functionalities within our body move and circulate and what powers that. Like, for example, think about our own blood supply system. What is in essence responsible for making sure that our blood circulates through our body? And it's our heart. And the earth is its own system, and it has very much a very similar process in what creates the weather and what allows the weather to circulate throughout the earth. So let's go ahead and move forward and start learning about some of this. All right, so in our overview, we're going to learn about um, first and foremost, atmospheric pressure. Pressure is what we consider to be of movement of winds up and down. So, right, we're all very familiar with winds that move left and right, right? The wind that blows your hair back or the wind that knocks down a tree. So that's a horizontal movement of air. Well, on Earth, we also have a vertical movement of air up and down. So that's where atmospheric pressure comes in. We're also going to learn about wind speed and direction, global wind and pressure patterns, local winds that we have, like for example, in the western United States and in Southern California, we have definite, very specific local wind patterns. We'll bring in why oceanic circulation is so important in these processes as well, air masses, and then talk a little bit about some of these weather systems as well. So let's go ahead and get started. Atmospheric pressure is pressure that's exerted by the atmosphere because of gravity on a column of air. So, for example, if you are in a low pressure environment, what does that feel like? It probably feels kind of nice. It feels relaxed, it feels calming, you're not stressed out. Okay. Now, in a high pressure environment, you feel like things are coming at you, right? A lot is coming at you. You're overwhelmed. It could be work, could be family, could be friends, it could be other things that are going on in your life. Well, pressure in the atmosphere, which, as we've learned about the various levels of the atmosphere, we live in that first layer of the atmosphere, which is called the troposphere, is when gravity is working on a column of air and it could be pushing down or it could be pushing down at various rates. So, for example, in Southern California, we get what is called extreme high pressure, which means that most of the time gravity is working on a large column of air that sits on Southern California and it's pushing down on a column of air. And when that is happening, that column of air doesn't move because it's being pushed down on. So that's one of the reasons why in Southern California we get a lot of smog because anything that we are putting up into the atmosphere, like our car exhaust, anything from factories, our air conditioners, anything that goes up into the air is being trapped because that high pressure is pushing down on that air and not allowing that air to move. Here is an example of what that might look like if we were going to visualize it. So for example, air is definitely more dense and less dense at various locations throughout the atmosphere. Now, at the lower elevations, we know that air density is higher because we know that when we go up in the mountains, we have to breathe a little bit harder because the air is less dense. So that is what this description right here is telling us. That air density is going to be more dense at your lower elevations, and you've got low pressure, and it's going to be low density. So as you go up in latitude as well, you're going to have more of a low dense environment. Atmospheric pressure decreases with altitude. as we know, when we go up in elevation, we've got to breathe harder. You actually have to cook a lot different as well because the air is different. Now, this affects wind speed and wind direction because if you've got one part of the United States or one part of California where gravity is pushing down on a column of air, well, if you're pushing down on that column of air, once it hits the Earth's surface, where is that air going? And that's where this idea of wind speed and wind direction comes from, because wind is created by high and low pressure. First of all, we know that wind is the horizontal movement of air. So for example, what does horizontal mean? Well, if you look out at the horizon runs from left to right. So horizontal movement of air means from left to right, and it is a renewable resource. Wind direction is named for the direction it comes from. So for example, when we get the Santa Ana winds in Southern California, that wind comes from the northeast. We don't call it a northeasterly wind, we call it a Santa Ana wind because when the people first originally moved and lived in Southern California, they knew the wind was coming from behind the Santa Ana Mountains and from around the area of the Santa Ana River. And that's the reason why it got named the Santa Ana winds. For example, if you're up in Oregon, they get a similar wind pattern and they just call those winds the easterly winds. Winds are named from the direction they come from. For example, a west wind blows from the west to the east, so it comes out of the west. Wind speed and wind direction are determined by three things, and we're going to be going over all three of these. Number one, wind speed and wind direction, so how fast it's going and where it's coming from, are determined by number one, a pressure gradient, number two, the Coriolis effect, and three, friction. And we're going to go over all three of those. Okay, so the first thing that affects wind speed and wind direction are pressure gradients. Now, when it comes to pressure, we've talked a little bit about what a high pressure center is and what a low pressure center is. Now, when you're looking at all of these lines are called isobars. Now, pressure is measured by barometers. So for that reason, we call these lines isobars. The prefix iso means the same or similar. So if you take the word iso, which means the same or similar, and add in the word bar, coming from the word barometric, you get this creation of a word called an isobar. So it means that these lines, which are isobars, are connecting similar levels of barometric pressure. So this is how we determine where our high and low pressure centers are. Remember, pressure is a vertical movement of air. And there's only two ways that air can go. It can be pushed down upon, so it can be moving toward the surface of the earth, which is what's represented in a high pressure center, or the opposite, a low pressure center, where the air is actually moving up into the Earth's atmosphere. We call that a rising. Low pressure centers are considered rising air. So moving up away from the Earth's surface and into the atmosphere. Now, what this red line is showing you is that, remember how previously I said that if you have a column of air that's being pushed down upon and that air is moving toward the surface of the earth, once it hits the surface of the earth, where does it go? Well, guess what? It moves then as wind. it becomes a horizontal movement of air. And it moves, this wind now moves to the low pressure center. And I'm going to show you an example of a visual example to help you understand how this works a little bit better. So wind always moves from a high pressure center to a low pressure center. That's a rule. It doesn't ever change. So here is a review of what an isobar is. And when you have isobars that are widely spaced apart, it means that your pressure gradient or your change in pressure is not as great. So the winds around this high pressure center are going to be not as strong. The more closely your isobars are together, which means you have a huge change in pressure, it means that your wind is going to speed up. So now we realize that pressure gradients are responsible for where the wind moves, so the direction of the wind. They're also responsible for the speed of the wind. So in this example, the pressure gradient or the change in pressure is the greatest closest to this low pressure center. And for that reason, the wind is going to be moving quicker or faster closer to this area, which we will call Memphis and Nashville. This image goes to show you how the earth gets heated up, what it gets heated up by, solar radiation. So remember how I've talked to you about how the sun is the energy source for 3 of our spheres. The lithosphere is not one of them. The lithosphere's energy is powered by the core of the earth. The biosphere, the atmosphere, and the hydrosphere are all powered by the sun's energy. How does this work? The sun heats up the land. The sun heats up the ocean, right? Heats up oceanic waters. And so then what happens here is that you have the sun, the solar radiation hits this land. Around it you've got water. And this heat that's created, so the earth soaks it up and it emits this solar radiation and re-radiates it back into the earth's atmosphere. Well, what's happening? We have air now that's moving up. What do we call air that's moving up or rising air? We call that a low pressure center. So here you can see how a low pressure center was created just by land being heated up. The second thing that influences wind speed and wind direction is called the Coriolis effect. Coriolis effect was named after a French mathematician. So I'm not going to really task you about knowing about this particular one in a very specific manner. All this goes to say is that the Coriolis effect is what happens to something that's moving on a moving object. What does that mean? The earth is always moving. Do we feel like we're on a roller coaster ride? No, we don't. We don't feel like we're moving, but the earth is in constant motion. And for that reason, anything that moves on the earth, for example, like the ocean and winds, they're going to be deflected because the earth is not a static thing. The earth is always moving. So it just means that winds that are going to be in the northern hemisphere are going to deflect a little bit to the right, and winds that are in the southern hemisphere are going to deflect a little bit to the left. Imagine that you're on a carousel and you take all the horses or you take all the whatever sort of things that you can ride on the carousel off, and it's just a flat surface. And you're moved, and it's like, okay, the carousel's going to start moving. And the carousel starts moving, and you take a ball and you want to roll the ball while you're moving on this carousel and going around, and you want to roll the ball straight to a friend that's on the opposite side of the carousel. You would notice that the ball would not go in a straight line because the ball is going to be forced upon to curve because it's going to feel the effects of being on a moving surface. And so that's exactly what happens here with the Coriolis effect as well. Now, the third item that affects wind speed and wind direction is friction. Friction, for example, friction happens when we have surfaces that could be flat, surfaces that could be hills, or surfaces that could have some sort of forest or rocks or mountains. So wind is always going to find the path of least resistance. So that's one of the reasons, like if you've ever driven out to Palm Springs, you'll notice that the winds really pick up in between the San Bernardino and the San Ysidro mountains. Why is that? Because the wind goes right through the path that you're driving on because the freeway goes through that path because they didn't want to build over the mountains. Well, the wind does the same thing. The wind is going to want to move in an area with the least amount of friction. So, for example, if you take this image here, you've got high pressure, which is a column of air that's being pushed down upon. That air hits the surface of the earth and moves away, and it moves towards the low pressure center. Low pressure is rising air. That air is moving up toward the atmosphere. So you have this natural movement of wind from a high pressure center to a low pressure center. The other thing that you will notice about how can you tell if you're in a high pressure center or a low pressure center is that high pressure centers are associated with clear skies. Why is that? The reason is because if you have air that's being pushed down upon, it's actually losing its ability to have any sort of water in it. Where the opposite is happening with low pressure centers, the air is moving up and it's losing its capacity to hold water. And therefore, clouds represent water in the air. So in low pressure centers, you know you're in a low pressure center when there's clouds. Like for example, if you were to go to Seattle or Portland, there's a lot of water in that air. So in that example, Portland and Seattle during the winter time also have a lot of low pressure centers. Southern California is dominated mostly almost year round by high pressure centers. That's also one of the reasons why Southern California gets very little rain because the winds are always pushing out and away. That means that it's deflecting any sort of weather that could possibly come in. Here is another great example of a high pressure center and a low pressure center. So what you'll notice here is the high pressure center is characteristic of wind or air that's moving down. So subsiding air that's moving towards the Earth's surface. You'll notice that the weather coming in from the Pacific Ocean is going right around that high pressure center, right around it. Then you'll see these winds are moving toward the low pressure center here. Low pressure centers are significant for rising air. You'll see the clouds here represented by air that's moving up. It's losing its ability to hold water, so the water condenses out as clouds. Here is when we start talking about atmospheric circulation. Atmospheric circulation is powered by the sun. So this is what we call the atmospheric circulation surface wind disk. So this is a disk that we study. Why do we study this? It's very important, and I'm going to start telling you why. You will notice that we have high pressure centers here, 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 and here, located around almost 30 degrees north of the equator and 30 degrees south of the equator. If you were to look at areas and parts of the continents that are located around these areas, you will find dry, dry, dry places. This is going to be represented by parts of the Mexican desert, the southwestern American desert. This high pressure center is going to be associated with the Sahara Desert. This high pressure center here is going to be significant for the Atacama Desert, which is located down in Bolivia and Argentina and Chile. This high pressure center is going to be significant for parts of Africa and also for parts of the deserts in the Nubian Desert, excuse me, the Namibian Desert, and for the deserts down in Australia. High pressure centers are associated with very little rain because you have gravity that's pushing down on a column of air and pushing away winds. How does this happen? How does this circulation disk even happen? How does it come about? Well, the first thing that happens is the sun. Where is the sun's solar radiation the most intense? It's the most intense along the equator. Remember when we learned about insolation and insolation rates? The most highly concentrated amount of solar radiation is in and around the equator. That's what starts this process in the first place. This is what fuels the circulation of our weather on Earth. So if we didn't have the sun, weather would stop. So the sun fuels many things that happen in our daily lives. So the sun hits at very intense rates in and around the equator and what we call the ITCZ. It's called the Intertropical Convergence Zone. So the sun hits in and around here. And then what did we learn previous to this about what happens when land or water are inundated by high amounts of solar radiation? That radiation is re-radiated back up into the Earth's atmosphere. Then you have air that's moving up. What do we have? What do we call air that's moving up or into the Earth's atmosphere? That's a low pressure center. So we have wind or air that's moving up into the atmosphere. It hits the tropopause and creates what we call a Hadley cell. So this wind, you'll see it moves up into the atmosphere. It's heated up, right, by the sun. Rising air, re-radiated back into the Earth's atmosphere, hits the tropopause, and it moves and it sinks back down. And where does this air sink? This air sinks in the northern hemisphere and the southern hemisphere around 30 degrees north and 30 degrees south. Now, what do we call sinking air? Sinking air is called a high pressure center. High pressure centers are associated with sinking air and few clouds and are dry locations. Where do you see this subtropical high? Right in front of the Sahara Desert. There's another one over here right in front of North America, and it's the reason why we have the Mojave Desert, the Chihuahuan Desert, the Sonoran Desert. Did I forget a desert? I can't remember. So, sun's insolation hits in and around the equator. That energy is re-radiated back up into the Earth's atmosphere. It rises, creating a low pressure center along the equator. So for example, if you look at a map today of weather in and around the equator, you'll see that the equator is almost year-round associated with clouds. Why is that? Low pressure centers are associated with clouds. This air hits the tropopause, creates this Hadley cell, and the air then sinks back down into the atmosphere, creating a high pressure center. Where does wind move? Wind moves from high pressure to low pressure. So you have this circulation pattern that is already created. So from the high pressure center, the wind is going to move from high pressure to low pressure and thus creating what we're looking at here, creating winds, global winds, and creating the ability of weather to move throughout the earth. This is how weather moves throughout our earth. Global winds are responsible for creating monsoon in larger continental mass areas. We have a monsoon here in North America, largely in the Southwest, in places like New Mexico, Arizona, and Eastern California. The monsoon is very significant in parts of Asia, so especially in India, Thailand, Southeast Asia. Here you're going to take a look at where some of these high pressure cells are located. So this one is located right in front of, this is the Namibian desert down here in Africa. This is associated with the Sahara Desert. There's also subtropical high pressure centers located on either side. Here in front of the Atacama Desert, and we have one over here that's in front of our North American deserts here as well, signified by, here you will see that high pressure center sitting over New Mexico, Colorado, Utah, Arizona, parts of California, and Texas. Here you will see the high pressure center here, the low pressure center here. Winds will move from this high pressure center to this low pressure center. So if you could answer this question, in the days of sailing ships, which pattern of navigation made most sense, considering the prevailing winds? So the interesting part about these global winds is that they also influenced the age of discovery, when people didn't have motors and all they could do was they were at the mercy of where the winds and the ocean currents would take them. So global winds also influence oceanic currents. So oceanic currents move in the same direction of these global winds. So for example, if you think about when these ships like Columbus or Vasco da Gama or Magellan were taking off from places like England, Spain, and Italy and Portugal, they would get in their boats, and these winds and these oceanic currents, where would they first take them? Well, they took them here to Africa. And what commodity was brought from Africa to this part of South America, brought to the Caribbean, and brought to this part of the southeastern United States? The slave trade. So these boats were first brought to this part of Western Africa. What population, what part of Africa's largest population was taken as slaves and brought to places like Bahia down in Brazil that has an 80% black population, while they were brought here by the Portuguese from West Africa to Brazil, to Haiti, to the Dominican Republic, to Jamaica, and also to the southeastern United States. So it's an opportunity for us to review now this global wind disk and how important this is. So we now realize that most of the sun's radiation is in along this ITCZ, which is called the Intertropical Convergence Zone. The air along this area rises and then sinks again in these very four large locations where we call these high pressure centers. Then winds from these high pressure centers move to low pressure centers up in higher latitudes and also back down into the lower latitudes, creating wind. This wind carries along weather, carries along storms, and carries along rains as well. Now, if we take an opportunity to look at local winds, so for example, the Santa Ana winds, most of the time our weather in Southern California comes from the ocean. That's why it's such a beautiful and amazing place to live. It's near the ocean, and most of the time our weather is dominated by the beautifulness of the Pacific Ocean, which means that the weather comes from the Pacific Ocean and to the continent, which means that most of the time our weather comes in from the west. Well, we do have this pattern, which is increasing, where we have weather that actually comes from the northeast and moves out toward the ocean. So you can see how this is affecting the Pacific Ocean. The weather, it's an opposite movement of weather, and we call this the Santa Ana winds. The Santa Ana winds are dry, sometimes they're cold, a lot of times they're very hot. It's because they're coming from the desert. And so we have an abnormal pattern where we have weather that comes from Nevada and it comes through Southern California because there is a high pressure center here and a low pressure center here. So it reverses that weather pattern that we usually always have.